complex integration. Under complex integration, we'll be dealing with contour integration, and we'll be using particular theorems. Cauchy's theorem, Cauchy's integral theorem, the residue theorem, and then it's the applications of contour integration. So let's start with Cauchy's theorem, which states that if f of z is an analytic function with a derivative that is continuous at all points inside and on a simple closed curve, then the contour integral is equal to 0 in C. The contour integral of f of z with respect to z. And note that we use that integral sign with a circle and a C at the bottom, which denotes an integration around a closed curve C in an anti-clockwise direction. I need us to understand that the integrand is the function f of z. In order for it to be analytic, then it means that all its poles must lie inside and on the simple closed curve C. Then we'll be able to say that we have used Cauchy's theorem. And then if the integrand is a quotient, then we're able again to restate Cauchy's theorem to be, in this case, we have 1 over z to the power n representing our f of z, and its integral, contour integral, is given by 2 pi j when the power of z is 1. But if you have any other integer as the power of z, then the answer is 0. Now we need to also note that if the contour does not contain the origin, which is a pole of the function, then the integral is 0. So if the pole, which is the origin, is not included in the contour C, then it means the integral is 0. Now let's look at a few examples here. We've been given an integral of 1 over z minus 2 as our f of z with respect to z, and it is equal to 2 pi j only if the contour C contains the pole z equal to 2. Taking us back to what we've noted there, that the pole must be included in C. But then if the pole is not contained in C, then the whole integral is equal to 0. Please note that all poles must lie inside and on the contour C. So if there's a pole that is not in the given region C, then the integral, that particular integral, where f of z has that pole, will definitely be equal to 0. Now example, the first one, we have to evaluate that given contour integral in the region given by the modulus of z plus 4 equal to 0.5. Remember, note that this 0.5 represents r, and we always have z minus z naught equal to r, and z naught represents the center of the given circle. So here we have z plus 4, which means it's z minus negative 4. So our center is at negative 4 and the radius is 0.5. But before we draw the region, let's go back and consider the integrand, which is our point of concern, and go and get the poles. Remember, it has to be analytic within and on the given region. So the first thing we need to check are the poles inside the region or not. So now we've got the poles, z1 equal to half and z2 equal to negative 1. The next step, sketch the region. Sketch the region and also indicate the location of the poles in the region so that we know which pole lies inside and which pole lies outside. Remembering also that when a pole lies outside or the pole is not contained in the region, that integral is equal to 0. Here is the sketch that we have. The center is at negative 4. The radius is 0.5. So from negative 4 to the right, it will be negative 3.5. And then to the left, negative 4.5. Then we go up. That means the circumference of that circle will correspond to 0.5 up there and to negative 0.5 at the bottom. And then we plot our poles. Z1 equal to 0.5 is right there on the right axis. Z2 equal to negative 1 is on the left axis, but both of them, they lie outside the given region. The given region is inside and on the circle. So hence we say both poles lie outside the given contour. Therefore, the whole integral is equal to 0. There is no need for us to evaluate it. B, now we are given a different region. We have to evaluate the same integral, but in a different region. Again, we sketch both poles because we've already calculated them. Note that here it's the modulus of z minus 0 equal to 3. So that means our center is at 0. The radius is at 3. So we do that. Center is at 0. Radius is 3. Now Z1 and Z2, for this region, they lie inside the given circle. Then we have to evaluate the integral. Note that the first thing I did was to use partial fractions to help so that I can be able to use Cauchy's theorem. Please verify that you will get A equal to 1 over 3 and B equal to 1 over 3 as well. And then immediately I get the partial fractions, I rewrite my contour integral as the sum of those two contour integrals. Instead of c, I write gamma 1 and gamma 2. And then I realize that I've got a constant in the numerator, which is 1 over 3 in both. And the highest power of z is 1. So I've got 1 as the highest power. And according to Cauchy's theorem, my answer is just 2 pi j. And it's 2 pi j multiplied by the constant that we find in the numerator. So it's 1 over 3 times 2 pi j plus 1 over 3 times 2 pi j, and you add them up and they give you 4 pi j over 3. We do this because both poles lie inside the given region. Now, another method that we could use also, which uses the first part of Cauchy's integral theorem, requires that we push one of the poles up, leaving one pole below, so that we formulate those f of z. Remember, it's got f of z in the numerator divided by z minus z naught, which is the pole. So that means we'll have here f1 of z represented by that numerator. And then that means the second numerator is f2 of z. So what we did, we left 2z minus 1 in the denominator and pushed z plus 1 in the numerator. So you still have z divided by z plus 1, all divided by 2z minus 1. Then in the second integral, we pushed the second pole up, which is 2z minus 1. And remember, it was dividing z. So don't multiply, but just push it up so that we have z divided by 2z minus 1 in that numerator. Now, our formula requires that we have z minus z naught, the denominator, which we have in both. We've got 2z minus 1 and z plus 1. And then the numerator is f of z. We have our f of z, which is f1 and f2. The answer then is 2 pi j multiplied by f of z naught. Note the z naught is the pole that has been left in the denominator. So our pole will get it from 2z minus 1 for gamma 1 and from z plus 1 for gamma 2. So let's evaluate. For gamma 1, the pole is half. f1 of z is the numerator, which is z over z plus 1. Then, in order for us to get a solution, we need to substitute z naught, which is that half, into f1. Not the whole function, but just f1. Then we got 1 over 3. And then we'll recall that the answer should be 2 pi j multiplied by f1 of z naught. And we got that answer for gamma 1. And then we go to gamma 2. f2 is the numerator, and the pole is negative 1. f2 of z naught, f2 of negative 1 is equal to 1 over 3. Once again, the integral is 2 pi j multiplied by f2 of z naught, and we get the answer 2 pi j over 3. And then we go back. We had said that integral that was given to us is equal to the sum of the two integrals in the regions of gamma 1 and gamma 2. We add what we got and we get 4 pi j over 3. I'm hoping you are noticing that in both methods the answer is the same. Remember, in the first method we used partial fractions, and now in this one we're using the Cauchy's integral theorem definition, and they both give us the same answer. Now we are on the residue theorem, which states that if f of z is an analytic function within and on a simple closed curve C, apart from a finite number of poles, then we have the integral of the whole function with respect to z equal to 2 pi j times the sum of the residues of f of z at the poles which lie inside C. We need to note that the poles must lie inside C. So first things first, when you're given a function or an integral to evaluate, one of the first things you do, determine the poles, sketch the region, and check whether your region contains the poles. And then you'll calculate the residues of the poles that lie inside the region, because those are the only ones that count. It must be the sum of residues of f of z at the poles inside C. Here is an example, same example that we used partial fractions on, and using Cauchy's integral theorem on. We're using it to check whether it's going to give us the same answer. Note that the region is the same, modulus of z equal to 3. Calculate the poles first. Both poles, if we drew that, remember we'd drawn that region, both poles lie inside. Then that means we have to calculate the residues for both poles. We start with half residue at z equal to half, and note that both of them are simple poles, so that means they have order 1. Therefore, we recall that we multiply the given f of z by the factor that gave us the pole, so that that factor will cancel the other factor in the denominator, and then thereafter be able to substitute half in. Please note, once you substitute here half in, you cannot write lim, and then we got 1 over 3. We do the same for the residue at z equal to -1. So the factor that gave us -1 is z plus 1. So we multiply z plus 1 to the function so that we eliminate the term z plus 1. So you are left with z over 2z minus 1, and that gives us an answer which is 1 over 3. And then it says that integral is equal to 2 pi j multiplied by the sum of the residues, and our answer is 4 pi j over 3. Number 2, we evaluate again the given contour integral using the residue theorem, and the region given to us is the modulus of z minus 1 equal to 1. Note the center is at 1 and the radius is at 1. So what I did was to draw the region, and then note the poles. One pole is at z equal to -pi, and the other pole is at z equal to pi over 2, and it's a double pole. We draw them. So -pi will definitely be on the negative side of the axis. and we have the pi over 2 inside. Using our calculators, we're able to realize that pi over 2 is less than 2, which is around 1.7. So the only pole that lies inside is pi over 2. So you need to state that, and then we use the formula for residues with order more than 1. We use the formula as it is, where our m is 2, so it's 1 over m minus 1 factorial, and the derivative is of that whole function multiplied by the factor z minus pi over 2 all squared, and it will be the mth minus 1th derivative. So we evaluate that, and we delete the term, and we are left with sine z over z plus 1. And we differentiate that before taking the limit, get the derivative, and we're using the quotient rule. Note that it must be denominator up first, multiplied by the numerator, minus the numerator times the derivative of the denominator. All of this is divided by the denominator squared. So what I did, instead of evaluating that, I went straight and substituted the limit, which is pi over 2, and simplify, and we got negative 4 over 9 pi squared. And again, the integral is 2 pi j times the sum of the residues, and the only residue we have is that one. We simplify and we get that answer. Here are some exercises for you to do, and I asked you, we use both methods of Cauchy's theorem and Cauchy's integral theorem, and as well as the residue theorem. Note that they must all give you the same answer. Then we will go on to the applications. The applications of contour integral, specifically onto real integral. So the first type that we encounter is where the integral is of a function of sine theta and cos theta integrated between 0 and 2 pi with respect to theta. One of the first things we need to do, because we're using complex analysis, and therefore we have to change everything to complex variables. So because we know sine theta and cos theta, they are always considered in a unit circle. Therefore, our z is equal to e to the power j theta, according to Euler's formula, which is cos theta plus j sine theta. And we also recognize that sine theta can be rewritten in exponential form, taking into consideration that e to the power j theta is equal to z. It would mean e to the power negative j theta would be equal to 1 over z, for the formula for sine theta as well as the formula for cos theta. So now we go to the method of evaluating this type of contour integrals. Step 1, into the integrand, substitute where necessary sine theta, cos theta, as well as d theta, noting that we're taking it directly from the derivative of z equal to e to the power j theta. So therefore d theta is equal to dz divided by jz. And Note also to change the integral sign. Remember, the integral sign given to us was the integral from 0 to 2 pi. So now we change it to a contour integral sign, and also noting that the full interval is from 0 to 2 pi. So if we have been given a half interval from 0 to 2 pi, that integral will be multiplied by 2. So it would mean, should you be given an integral of that nature, that means the full integral will be multiplied by half. And then the next step, simplify the expression and determine the poles. And thereafter, step 3, use the residue theorem to evaluate. So it's very important that you do the correct simplification, correct substitution, correct simplification, correct calculation of the poles, so that we can be able to calculate the residue. Also remember the unit circle. That means the modulus of z equal to 1 is our C. Need to always remember that for these types. Okay. Let's do an example. We've been given the integral of cos theta divided by 3 plus 2 cos theta d theta, and we're evaluating from 0 to 2 pi. That's the full interval. That means full circle of radius 1, center 0. First things first, we have to substitute cos theta and cos theta as well as d theta. We substitute them in, and then we do the evaluation. Please keep checking whether I've not made any mistakes here. Evaluate. So the first thing I did was to simplify the numerator, also simplify the denominator, leaving dz over jz there, and then I took out 1 over j as I simplified that quotient, giving me z squared plus 1 all divided by 2z into 3z plus z squared plus 1, which you could write it as z squared plus 3z plus 1, and then did the factorization straight from the calculator, and we got the factors as well as the roots. So we've got those two roots from z squared plus 3z plus 1, and we know 2z, or should I say z, is giving us a pole which is z equal to 0. So we've got those 3 poles. Now to remember, our C is the absolute value of z equal to 1. And with this, we must check whether each of those 3 poles lie inside modulus of z equal to 1. All you need to do is just to punch to our calculators and see which one was inside and which one is out. So I know that z equal to 0 and z equal to negative 3 plus root 5 all divided by 2 are the only 2 that lie inside, that have got length less than 1, and the other one is bigger. Hence we say here only those 2 poles lie within, and then when we know those 2, then we only calculate the residues of the poles that lie within the unit circle, and I got half for the first one, and I got negative root 5 over 10 for the second one. Then we remember that we'll have 2 pi j multiplied by the sum of the residues, but then we have to recall that we had taken out 1 over j in our simplifications. So we need to recognize that there is 1 over j outside as we simplify. And then that was what we were able to get. Let's check the steps. First things, substitute cos theta. And cos theta, as you change it from a real integral to a contour integral, and also change dz, and then simplify, and then calculate the poles, and then check the poles that lie within a circle of radius 1, and then find the residues of those poles, noting that the integral, or the given integral, will be equal to 2 pi j multiplied by sum of those residues. We go to type 2. Now for type 2, we have a function of variable x, and we're integrating it with respect to x, and it's an infinite integral from negative infinity to infinity, the full integral. One of the first things that we need to recognize that it has to be changed to a function of z, and the integral sign be changed to a contour integral in order for us to be able to evaluate. And thus the region we're talking about is a semicircle, gamma, which has got radius r, and is a semicircle on the upper part or upper half of the z plane. And we know that on the left we'll have negative r, and on the right we'll have r, because we said the semicircle is of radius r. Note that we don't know the specific values of r as we evaluate. As we move, we recognize that our region of consideration is given by that sketch, noting that on the x-axis we have the radius as well as the contour gamma on the upper half of the x-axis. That means occupying quadrant 1 and quadrant 2. Now the contour integral recognizes that there is a region function of x on the x-axis between minus r and r, as well as the semicircle, that is the contour itself, f of z around gamma. Now the step 2, we need now to be cognizant of the fact that as r approaches infinity, that means as you stretch your radius, the contour flattens. That is why the integral of f of z dz in the region gamma becomes 0 as r approaches infinity. Therefore, you end up with that contour integral of f of z dz just being represented by the first integral as r approaches infinity, because we eliminate the second one only as r approaches infinity. Once we've gotten to this step, we make use of the residue theorem to solve the contour once again. Please take note that one of the steps that is required is that contour integral being the sum of those two integrals, and then recognizing that r, as r approaches infinity, the second integral becomes 0. And therefore, please remember to write that limit as r approaches infinity for the first integral. Let's do some examples. I'll just do one example and then I'll give you some exercises. The example that I've chosen here is 1 over x squared plus 4 all squared being integrated with respect to x between negative infinity and infinity. So that's the full interval. Then, as I noted, we need to write that sum. Remember, it's f of z on the left, f of x as the first integrand, and f of z as the last integrand. Noting that the first integrand on the right hand side is between minus r and r, and the second one is just the contour gamma. And then to eliminate that last integral, we need to recognize that as r approaches infinity, that semicircle flattens. So that means the region under that curve diminishes, so it becomes 0. Therefore, the limit as r approaches infinity, because we said it diminishes as r approaches infinity. So as the limit of r approaches, limit as r approaches infinity of the first integral with respect to x between minus r and r will be equal to the contour integral. And we are able to evaluate the contour integral using the residue theorem. So we go for the poles, so it factorizes. We need to factorize the denominator. And then thereafter, get the poles, noting that we are getting double poles because of the all squared that we're given. And note that we've got minus 2j and positive 2j. Minus 2j is on the negative side of the y-axis or imaginary axis, and 2j is on the upper, which is positive side of the imaginary axis, and noting that the semicircle is above the x-axis, so only 2j lies above the semicircle, so above the x-axis, which is in the semicircle. So therefore, we're going to calculate the residue as at z equal to 2j. Then thereafter, after doing the calculations, and then we know that we'll multiply our residue with 2 pi j. Also, remember, it's a double pole, so that means there must be differentiation. Deleting those two, and you are left with that term that needs to be differentiated, and then thereafter you do the evaluation. Here are the exercises that you can do. The full interval for number 1, full interval for number 2. This number 1 is type 1, number 2 is type 2, and number 3 is also type 2, but now we gave you half the interval. Please recognize that.